In this video, we will talk about how we can use mods to do computations. So I want to start with a theorem which says let a, b, c, and d be integers, let m be a positive integer, and let a be congruent to b mod m. Remember what that meant was that both a and b have the same remainder when I divide them by m. Or an equivalent way to say that is that m will evenly divide a minus b. So if that's true and c is congruent to d mod m, meaning both c and d also have the same remainder when divided by m, well then it turns out we have the following three things. So if you add the left-hand sides of these together, a plus c, that's going to be congruent to if you added the right sides together to get b plus c. So those will be congruent to each other, mod m. Okay, and then similarly for subtraction, if we subtract the two sides, and also it turns out you can sort of multiply these two things together to get AC is congruent to BD mod M. Okay, so I want to be careful in that there's no statement like these, either for dividing two of these things or rooting them, because when I do either of those, these don't necessarily yield integers. So a divided by c won't necessarily be an integer. Same with square root of a. Whereas with all of these, they will be. So that's one of the ways I can kind of automatically rule these out. So I won't do the proofs of these statements. Instead, I want to focus this video on how to apply them. In a later video, I'll show how to do a proof of one of these congruences type things. So the example says compute 62 plus 118 mod 6. So I'm going to do this in two ways. First, I'm going to do it directly, recalling, well, what does this mod notation mean when it doesn't have the congruence symbol? Remember, all that means is whatever this is, divide it by 6 and tell me the remainder. So, well, okay, let's add those numbers together. So adding 62 to 181, I get 243. And I want to know what's the remainder when I divide that by 6. Well, I could work this out. 6 multiplied by 40 gets me to 240, and I'd have to add 3 to get to 243. Okay, so what that means is what this remainder is, well, it's just 3. Okay, I might have to think about this a little bit. I had worked it ahead of time, which is why I could do it more quickly here. So, okay, what's another way I could have worked this out? So I can use this previous theorem. So what the previous theorem says is, well, let's figure out what each of these things are congruent to. So 62, when I think about that mod 6, it's congruent to 2. So that means the numbers 62 and 2 both have the same remainder when I divide them by 6. Well, 181, what would the remainder of that be if I divide it by 6? Well, it would be 1. So 181 would be congruent to 1. So this is saying that 181 and 1 have the same remainder when I divide them by 6. So what the theorem says is now I can sort of add these together. So if I do that, I'll get 62 plus 181 on one side. And that's congruent to, and I can replace 62 with what it's congruent to, which is 2. I can replace the 181 with what it's congruent to, which is 1. And then I write my mod 6 in parentheses. So this left-hand side has the same remainder as this right-hand side when I divide each of them by 6. Okay, and well, 2 plus 1 becomes 3. Okay, so in terms of the answer to my original question, again, when I write the mod like this, and there's no congruence symbol, that just means whatever this number is, and I divide it by 6, what's the remainder? So now at this point, I know that, well, the remainder is going to be the same thing as whatever 3's remainder is when I divide it by 6. But that's just 3. That's just 3. That is just 3. All right, cool. So let's end this video with one more example where we up the difficulty and we really start to show some of the power of these mods. So let's find the last digit of 2019 to the 2020 power. So when I think about the last digit of something, I can get that by thinking about a remainder. the last digit of something, like if I think about the number like 81 or the number 75, the last digit is whatever I get when it's the remainder of what I get when divided by 10. Remainder when dividing by 10. That'll tell me this last digit. Okay, so in other words, we have to figure out what this remainder is. And that suggests maybe I'm going to use mods, because mods are so great when trying to calculate remainders. All right, so before I get into the power, let's focus on this number 2019. And I'm going to notice that 2019, ultimately I need to know a certain remainder divided by 10. So what is this congruent to? Mod 10. What does it have the same remainder as in mod 10, but maybe a simpler number? Well, it's got the same remainder as 9. I can see that because that's the last digit. It's got the same remainder as 9 in mod 10. So, okay, I can even simplify this further. I mean, not only is that true, but like, this would also have the same remainder as like 19 mod 10 or 29 mod 10. Anything that ends in a 9 like that, where I keep adding 10 and I keep adding 10 to these. But I can go in the other direction. Instead of adding 10, I could subtract 10. And that's nice because then I get, if I subtract 10 from the 9, I get -1. So this is congruent to -1 mod 10. Just as a check for why that is, remember the definition of this congruence symbol means, well, if I take the 10, will that evenly divide these two things subtracted? Will that evenly divide 9 minus -1? Well, yeah, 9 minus -1 becomes 10, and 10 divides 10. So I'll put a check mark. Okay, so that's why it's okay to say that this is congruent to -1 mod 10. So thus, if I'm trying to now compute 2019 to the 2020 power, well, this is congruent to. This just means 2019 times itself a bunch of times, times itself 2020 times. 2020 times. That's how many times I'm multiplying this by itself. But the power of congruence says, well, I can replace each of these things, because I'm doing a multiplication, with what 2019 is congruent to. And I know now that it's congruent to -1. So I'm going to replace each of these with the -1. So I'll get -1 times -1 times -1, 2020 times. Okay, so, all right, so this is congruent to -1 to the 2020. I'm getting a little bit sloppy here. I've stopped writing my mod 10 at the end of each of these lines, but I should. So this was happening mod 10. This was also mod 10. This was also mod 10. Okay, I think I'm one step away. Well, what's -1 to the 2020 power? Well, that's just 1, because it's an even power. So this is congruent to 1 mod 10. So what this shows is the thing that I started with, 2019 to the 2020 power, ends up being congruent to just 1 mod 10, meaning they have the same remainder when we divide them by 10. Well, what's the remainder when I divide 1 by 10? It's 1. Okay, so that means my last digit is just 1. Okay, so this is one of the ways in which mods can drastically simplify calculations like this. One of the key things that this example kind of illustrates a specific case of is the following theorem, which says if a and b are integers and m and c are positive integers, then if a and b are congruent to one another, mod m, like I had 2019 is congruent to -1 mod 10, it turns out that we can raise both sides to a power, both sides to the c power, and they'll still be congruent. In fact, we kind of have that here. This whole thing to the 2020 ended up being congruent to -1 to the 2020. We actually showed why this was true by doing this calculation. Okay, so that theorem says this is true in general.